Assalamualaikum, good morning, good afternoon, good evening, or good night. BEKU 2333 Electrical Circuit 2, still in the chapter Frequency Response, and today we're going to discuss about filters. A filter is a circuit that is designed to pass signals with desired frequencies and reject or attenuate others. Passive filter consists of only passive elements R, L, and C. There are four types of filters, namely low-pass filters, high-pass filters, band-pass filters, and band-stop filters. Ideal frequency response of the four types of filters. In a low-pass filter, it is designed to pass only frequencies from DC up to the cutoff frequency omega C. It looks something like this, in which all frequencies below omega C is allowed, while frequencies greater than omega C is disallowed. For high-pass filters, it is designed to pass all frequencies above its cutoff frequency omega C. Referring to the graph, omega C frequencies greater will be allowed, but any frequencies below that will not be allowed. For a band-pass filter, it is designed to pass all frequencies within a band of frequencies ranging between omega 1 and omega 2. And it looks something like this. Any frequencies in that range will be allowed, while others will not be allowed. For a band-stop filter, it is the opposite. It is designed to stop or eliminate all frequencies within a band of frequencies omega 1 and omega 2. So it looks something like this. All frequencies between omega 1 and omega 2 are disallowed, while all other frequencies are allowed. This is the table of summary, showing the type of filters: low pass, high pass, band pass, band stop, and also H at 0 and H at infinity. Right. So we're going to discuss two types of filters. One is passive filters, which only contains elements R and C, which are passive, and active filters, which consist of transistors, operational amplifiers, in addition to passive elements. Now, the passive low-pass filter looks simply like an RC circuit, and the output is measured across the capacitor. And looking at the transfer function, the V out over V in, we have this, which was previously discussed, results to 1 over 1 plus j omega RC, and we have a transfer function graph which shows omega C, a cutoff frequency at 0.07 h omega magnitude, and we know that this area which is less than omega C is the ideal area in which the frequencies are allowed. And to get the cutoff frequency or roll-off frequency omega C, it's simply 1 over RC, because we know that at 0.707 there is also 1 over square root of 2. Low-pass filter can also be formed when output of RL circuit is taken off the resistor. That means the output V out is measured across the resistor. For a passive high-pass filter, the circuit is RC and the output is measured across the resistor. Thus, we have a transfer function which shows j omega RC over 1 plus j omega RC. And looking at the transfer function graph, so it becomes a high-pass filter when frequencies are greater than omega C, the ideal condition. It's allowed 1, and when it's less, then it's not allowed. The actual one has a slightly different shape. And to get the cutoff frequency omega C, it is the same equation, omega C equals to 1 over RC. A passive band-pass filter consists of RLC circuit in series, but note that the output voltage is measured across the resistor, and thus we have an output transfer function which shows R over R plus j omega L minus 1 over omega C, and this becomes a band-pass filter as shown. and omega 1 omega 2 cuts off between 0.707 magnitude, and the resonant frequency is at 1 over square root of LC. Half power frequencies, bandwidth, and quality factor can be calculated using the formula in the series resonance circuit. For a passive band stop filter or band reject filter, sometimes it's called notch filters, it is the same RLC circuit, but this time the output is measured across the inductor and the capacitor. And we have the transfer function as shown, j omega L minus 1 over omega C over R plus j omega L minus 1 over omega C. And you will see a shape like this, in which all frequencies between omega 1 and omega 2 are blocked or stopped. And the resonant frequency omega 0 is 1 over square root LC, and it can be calculated for bandwidth quality factor using the formulas that we learned before. Omega 0 is called the frequency of rejection, and B is called the bandwidth of rejection. For a general first order active filter, imagine that we have this kind of circuit, and there is a impedance ZF feedback and ZI for the input impedance, and we have an operational amplifier which is inverting. The components selected for ZI and ZF determine whether the filter is low pass or high pass, but one of the components must be reactive. For an active first order low pass filter, circuit is as shown. The feedback impedance has RF and CF, and the input impedance only consists of RI. And the transfer function is V out over Vn or minus ZF over Zi. Why minus? Because it is an inverting amplifier. And Zi equals to Ri. Thus we have Zf, which is simplified to become Rf over 1 plus j omega Cf Rf. And this transfer function is the same with which we get a passive low pass filter, only it has a DC gain minus Rf over Ri at omega equals to 0. To get the resonant frequency, omega C equals to 1 over Rf Cf, and it does not depend on Ri. For an active first order high pass filter, we have the circuit as shown, Rf and Ri. This time in the input we have Ri, which is in series with capacitance. Hence we have the transfer function V out over Vi, which is minus j omega Rc over 1 plus j omega Rc. And the transfer function is the same with which we get passive high pass filter, only it has a DC gain at minus Rf over Ri. The resonant frequency is omega C equals to 1 over Ric. Right, the active band pass filter is a combination of low pass, high pass, and inverter gain. It starts with the low pass, which selects the omega 2 value, and then it's connected in with the high pass filter, which selects omega 1 value, and in the end an inverter which provides the gain and also to invert the output. So this is generally how it's done, and the transfer function is V out over Vi, and it is as shown in the equation. And we have at last a band pass filter with omega 1 1 over Rc2 and omega 2 1 over Rc1. You note that omega 0 resonant frequency is at square root of omega 1 multiplied with omega 2. In case again, which is Rf over Ri times omega I over omega I plus omega I. Right. For an active band reject filter, this is the circuit in which the low pass and high pass filters are connected together before going to the inverter, and this produces an output transfer function as shown, and it will produce a band reject filter between omega 1 and omega 2. The gain, negative k, is negative Rf over Ri, and transfer function is as shown. So in the end, this low pass filter and high pass filter sets are being summed at the amplifier, and it's just a matter of adding V1 and V2 from low pass and high pass filters. So example number 1, design a passive band stop filter with the specification below. We have F0 equals to 200 Hz, B, which is the band which is 100 Hz, given R with a value of 150 ohms. So it is a series resonance circuit, and remember that the output voltage is across L and C. So we have L, which is R over B, and that is 150 over 2 pi 100, and it will give us 0.2387 Henry. And for the omega naught, it is simply 2 pi f naught, and that is 400 pi radians per second. And for our resonant frequency, we can find C, which is 2.66 microfarads. The application of filter is in the crossover network. So it is a circuit that couples an audio amplifier to woofer, low frequency 3 kHz loudspeaker to low pass filter, and tweeter, high frequency loudspeaker to high pass filter. This is a circuit or crossover network with 2 loudspeakers. It has a tweeter and a woofer. An equivalent model by replacing amplifier with voltage source and speakers acts as R. For the tweeter, the transfer function is V1 over Vs, which is j omega R1C over 1 plus j omega R1C. And for a woofer, it is omega 2 over Vs, which is R2 over R2 plus j omega L. The frequency response for the crossover network is as shown. We have 2 transfer functions, and in the middle is omega C. R1, R2, and L and C must be selected such that 2 filters have the same omega C. And R1 and R2 are always given depending on type of speaker, and LC can be calculated by omega C 2 pi fc 1 over R1C for high pass filters, or for low pass filters omega C equals to 2 pi fc, which is R2 over